Okay, here we go. So you need to get the vector problem set out, and this could be pretty boring for certain segments for people in video land, because I'll be sitting here going, all right, I'm waiting for somebody. We are going to look at 17. So what I need is for somebody to read through 17 and then come up, and all I would like you to do is draw a picture. And remember, these are vector problems, so there will be directional things and arrows in the picture, but I want you to draw me what you consider to be the correct representation of that problem on the board here. And then we'll talk about, well, how the heck do you go through and solve all this stuff? So as soon as somebody wants to come up here, somebody watching this is probably, is the volume on? Volume?
I'll do it.
Okay, so any color or combination thereof. Oh, and while Anthony's doing this, one of my comments, and when I'm looking at your work in general, for those of you who really used up a decent amount of space to do your sketches, that was much appreciated, because sometimes I thought people were trying to get like extra points for trying to cram the most crap into the smallest amount of area possible, which made things really, really challenging to look at sometimes. Okay.
Wow.
Now, I'm going to say that for the information given, we got everything in there. Now, in order to attack this, there are a couple things that we need to kind of acknowledge. Our two dimensions, even though they, I always hate it when they use north, south, east, west. It's always good so we can see who knows their directions. But the truth is, we always have to turn that into a mathematical thing. So even though the problem is doing this, we need to remember that when it comes time to do math with this stuff, we need to remember our angular, our polar coordinate type angle. And we need to acknowledge some things about how things move in each dimension. Because previously we said that when two vectors or two dimensions are perpendicular to each other, that means they're independent from each other. And that means what happens in one dimension does not impact or influence what happens in the other dimension. And that's why when we did projectile motion, we said in one dimension we had constant velocity motion, but then in the other dimension, vertical dimension, we had acceleration happening because gravity got to act on things vertically. But that did not influence what was happening horizontally. So when it comes to this particular problem, when we focus on just the horizontal dimension, what kind of motion are we playing around with here between the constant velocity, accelerated motion? Who can give me an answer on that one?
What kind of motion?
Yeah,
Constant?
it's constant. The only thing we have in the horizontal dimension here is the river, and it says it flows like that all the time. So that means in the horizontal dimension, we are playing around with constant velocity. What equation does that mean we use here?
Delta x over t.
Okay, it means we use this. In math, they might do like d over t. We use a delta something. Since this is in the horizontal dimension, which we call the x dimension, we would use delta x over t, and then what would we add here to make it more specific for the horizontal dimension?
V of x.
It would be v sub x. So the only thing we can put in there is something that is only in the horizontal dimension. What do we have it, at least because of the way the picture is drawn, what's happening in the vertical dimension here?
Also constant velocity.
It is also constant velocity, because what's the thing in the vertical dimension in this picture?
The boat moving.
Just the boat. And it says the boat moves at a steady rate. So in this particular problem, we also have constant velocity in the vertical dimension. So what is our equation for the vertical dimension?
V sub y is delta y over t.
Very good. So instead of delta x, we use delta y, and that isolates only movement that's in the vertical dimension. Okay, now that is important. When you go from one problem to the next, this idea of trying to assign what kind of motion or what do I have in the different dimensions is important, because when we do projectile motion, one dimension is constant, the other one is acceleration, and that means we have a whole bunch more stuff that we have to maybe worry about. Okay, now in my picture here, if I were to just ask you, because most people already have this sense, which way is the boat going to go? And when they say with respect to the shore, it basically means somebody on the shore watching all of this happen. When this boat tries to go across the river with this stuff going, what direction is this boat going to head in?
East.
Northeast?
Okay, so you'd go like this. Somewhere over there then. And if I go y, give me the vector explanation for it.
As it's moving north, it's being pulled east by the current.
Right. If you ask the boat, hey, what are you doing? I'm going this way. It doesn't, in a sense, recognize this in and of itself. And when you ask the river, hey, what are you doing? I'm just going that way. It doesn't care about the boat. The boat just gets pulled with it. So it's the combination of these two that makes it go that way. So here's where I'm going to ask for another volunteer. I want you to draw me the vector triangle that explains that and label it. This is the part where I'm going to say, how am I supposed to know to do that? Hopefully after playing around with vector crap for 2 weeks, you can go, oh, I know what you're talking about.
I can try.
Go for it. You can draw the triangle and then label anything you want on that triangle. And you don't have to do it within the picture. You can do it above or below the
Should I
picture.
just use one color?
Yeah. Or, unless you want to match the color coding that Anthony started, you could do that as well.
Match me.
Nice. Okay. Now, what if I asked you, go ahead and label the ones that you know, like number-wise. Which arrows in your picture do you know? Yeah, that's what I'm... Okay. Perfect. All right. Now, if you were already kind of thinking of something like this, excellent. That's why I have people play with just vectors. So when someone says, make me a vector triangle, they get the idea, well, I gotta connect a bunch of arrows tip to tail. And one of the beautiful things is, if I went based on scale, do I have a real good drawing? I'm being snarky now.
Kind of.
Yeah, well, what would I have to adjust if I said, okay, that's really not pointing in exactly the way we're going to go, but we're going to figure that out mathematically, and that's where our accuracy is going to come from. What would we do with either one of these? If we said, could you make your picture a little more accurate?
Shorten the blue one.
We'd either shorten the blue one or
Lengthen the black.
lengthen the black one so that we have a scale between the two. But again, that's the beauty, that if you can just make this sketch, we are good to go. Because now if I ask, where's our answer? What are you going to point to in my picture? The green arrow, which we would call what in traditional vector terminology?
The resultant.
The resultant. And if I say, well, how the hell are you going to get that one now? What could you spit back to me? Super quick.
Add the blue vector. Or
I'm looking.
Pythagorean theorem.
Step 3, step 4, done. And step 3 is Pythagorean step. All right. Step 4,
Step 4 is inverse tangent.
arctangent step. What quadrant are we in?
1.
Okay. Then this is where I did not ask you to do this, but in your picture, when you go to do something like this, I would say, like, label the theta, and this is where I had too many people labeling the internal angle for this, which is not the one we're looking for. It's that one right there, okay? Because when people say, oh, why don't we do the internal angle? That can vary what quadrant you're in. You need some, uniformity. So when you go for theta, it's always measured around from 0 degrees. Okay, so if we look at this now, and we go back to these guys over here. What variable is my 10 meters per second?
P1.
Oh, wait. Oh,
What's my 1.5?
yeah.
Okay, so that means what's the other thing that I need to identify in here then? That'll allow me to start to solve for crap over there.
Delta. And Y.
Okay, now, if this is where I ask, don't give me numbers, just tell me what you're going to do. I'm going to solve for t here, and then what do I get to do with that?
Use that to solve for delta x.
I get to bring that over here. All right? That's the idea. If you're going, I can see that. That's awesome. Okay, the only thing I don't allow you to do is, I'm just going to do it on my head and just, put numbers down on a piece of paper. I'm not gonna bring up a certain business about I disagree with that approach. What's the number that we get for t? Because you can do this one in your head.
30.
We get 30 seconds. We bring that over here. What is our delta x?
45.
45. Okay, now here is another cool thing about vectors that I'm going to bring up. if I were to do, I would call this triangle a velocity vector triangle. But I can make another vector triangle out of this problem now that I have everything solved. And it would be a displacement triangle. And it would look, I'll use the same color coding. It would, and I'm going to do it right next to this. It would look like this. Where's my blue? I'm going to go with this. But if I was doing this based on displacement, what number would go with this black leg? This triangle.
300.
Oh, yeah.
Very good. What would go with my blue?
45.
Okay. Now, we haven't figured out this green one yet? Yes?
Why couldn't we just use the 10 meters per second and the 1.5 meters per second on the Pythagorean theorem to find its normal speed, and then once you have all three sides of the right triangle, you can just use the trig functions to find theta.
Isn't that what we did?
When?
When we went for the answer, when we went for this green one, it was the Pythagorean.
Did we find it yet?
I don't know. I just told you that's what you would do to find it.
Oh.
And then to find the angle of it, you would use the arctangent step based off these two.
Oh, wait, so then how come we're doing all the other stuff?
Ah, that's why. Let me add this to the picture. Guess how many degrees that is?
Same.
It is exactly the same number of degrees as this. But how is this triangle different from this one?
It's bigger.
What are we measuring in this?
Delta x.
We are doing displacements. We are basing this approach of what the boat is doing based on how far is it going. This is based on how fast is it going. But the beauty is, what would we say about these two triangles from a math perspective? They are similar.
Wow.
So now, what's the incorrect word to use that did pop up in one class? Congruent. Because they are not congruent because they have different values. But they are similar triangles because the rate that you're moving at and how far you've gone, those have the same relationships to each other during the course of the problem. That, if you get it, is a cool higher end concept with vectors. Okay, now I have one other thing, one extension here that I'm going to ask somebody to draw down here. Because in our problem, our boat captain went ahead and said, I know I'm going to get dragged down by the current, but I want to get across the river as quickly as possible, so I'm just going to point myself directly across, let the current take me, and get across in 30 seconds. And I don't care if I'm 45 meters downstream, I'm cool with that. Now, I want somebody to draw me a vector triangle that would cover a situation if the boat captain said, I can go 10 meters per second, but I do not want to get dragged down by the current. So I want to compensate for the current so that as I move through the water, I am going directly across the river. So that when I'm finished, I will land right across from where I started. Can someone draw me that triangle?
I can, but I already drew one.
Anybody else want to?
I'll do it.
Okay. This way. We'll see if it's right. Okay, now, before you go, I have one beef with that. One of those arrows is incorrect. Which one?
This one?
Oh, I take it back. Hold on. No, I could roll with that. Okay. Yes, I'm good with that.
Okay.
Okay. Now that, well,
Well, I think that you should cut out the last like 30 seconds because Johnny said his
No,
social
I didn't-
security
I
number.
didn't actually. It was not my
No,
actual
it
security
sounded
number.
like he said it.
No, it was not my actual security number.
I think he's lying.
I swear on my
Okay.
No, I think he
Now.
actually said it.
I swear on
we're
my
good
life.
with the picture,
I swear on Genevieve's life.
but there is one number that's not in the right spot.
Oh, the 10?
Where should the 10 go?
On the green.
Correct. So what I'm going to do is I'm going to change your black and your green, okay? This is where we're going to have that discussion. Okay. So here is the deal. That now let me ask this: why does the 10 have to go here?
Because that's how fast the boat's moving.
Correct. Because now the boat captain has said, "Hey, I want to go straight across." Again, intuitively, based on the picture, people would say, "Oh, well, you should point yourself upstream." That's what you did. But it said the boat moves at 10 meters per second. So when you point yourself upstream, you still can only go 10 meters per second. So that's why it's not this one, because the green one represents what the boat is actually doing. Now I'm going to come back to that in a minute. Now, technically speaking, I'm going to put an alternate arrow in here. Because this 1.5, what does it represent?
The speed of the current.
The speed of the current. Well, actually, I'll do this. I am going to break this black one into a horizontal and a vertical. So if my 10 meters per second is my V, this would become my Vx, and this would become my Vy for my boat. Can you use this picture to explain to somebody why the boat is going to go straight across the river now? Because it's in the picture. Who can connect it? You're just making a hand motion, not a like I know.
She knows. She just wants to tell us.
What's the blue represent? The current. The water actually going downstream. We don't want that to happen. So what do we have in the picture?
The opposite.
Guess how big this is?
Oh, 3 meters per second. Is it also 1.5?
It's also 1.5. But what's different about this 1.5 and that 1.5?
One's negative.
So they add up to
0.
0. So that means you're not going to move one way or the other in the horizontal dimension.
I was thinking of it as there were like 3 apart.
Oh.
Because it was like positive.
Now, this is another cool question about this. Compared to what we found before, how long is it going to take the boat to get across? Less, same, or more?
Not more time.
More?
It takes more time.
Why?
Because you're going against the current instead of letting the current like. Oh wait, no, it's the same, right? I don't know. I thought
More
it would
time,
be the same.
you
but-
have less speed forward.
Oh.
How many meters per second did we have here oriented directly across the river when we said screw it, I'll let it take me down?
10.
We had 10. How big is this red leg now? Because we're using a little bit of our 10 to do this, what happens to this compared to 10? It goes down. So that means our velocity oriented across the river compared to 10 is less than 10. And therefore, we still have 300 meters that we got to get across, so it will take us a little bit longer. With the benefit of not getting pulled downstream. Okay? These are the subtle things with vector stuff that if you're like, oh, I get that. Though, that's like, okay, I understand what's going on here. Okay. That's good. And that's like a part C that wasn't even asked though. Okay. So now somebody read 18.
We have time for 18.
Yeah.
What?
Read 18. It's another river one. So the truth is, if you're going like, oh, I kind of get this,
Read it or draw it.
read it, and then if somebody's ready to draw it, I will take anybody who wants to draw it.
I think it's Gigi's turn. Or unnamed person's turn.
Oh,
I think that the person who said this is what security number was.
Okay, I'll do it then.
all right.
So was your real social security number?
No. Was not.
Okay. Let's see what you come up with.
Okay. So I'm gonna take a. I'm gonna do the same coloring as Anthony.
All right.
The original. Because water is. Okay. So, we got a boat that is.
Why is the river so big?
Doesn't matter. So, crossing. So it's going this way because it's like north of west, 62 degrees. So that's like I'm not getting to. It's like. And then
And which way is it headed? So an arrow on that. Okay.
Okay. Velocity. Three. It's too small. That might be too big. Okay. Oh, I gotta label my angle. Wait.
Go ahead and label it the way it's described in the problem,
Okay.
and then we'll have a discussion about that.
River. I guess I'm going to represent the river. Eastward current. Okay. Okay. Good.
Okay, that's the picture. Okay. So, getting into identifying stuff. What is our 0.505 here?
Delta Y.
Okay. What is our 1.25?
The current.
Okay. Okay. We'll put here current. You want to name it anything, like with variable wise?
I thought we were. VX.
Okay. Okay. What's different about this one?
With the angle.
What?
With the angle.
We have an angle. What does that mean we need to do? We didn't have to do something in the last problem that we're going to have to address here because of that. Okay, what do we call that?
Resolving.
We need to resolve this vector. So, this red arrow, instead of looking at it as it's drawn, which is correct, we need to rethink of it as, I'm going to go this way, and then, okay? And in doing so, what do we have to make an adjustment for over here in the picture? What are the equations we use for doing this? What is it that we have to do?
Like use a different trig function or something?
No. I'll tell you if I ask most people, okay, you're desperate, do something. They'll go in and go, all right, I'm going to put 62.5 in there. Very good. When we are doing our vectors, our angle is measured all the way around. Anybody do that one in their head?
One, 117.5.
117.5 degrees. So now we have 117.5. That's going to go here. That's going to go here. And that allows us to calculate this thing that we would call Vy and Vx.
Wait, I have a question.
Yeah.
How come like the origin is at the top of the bow instead of like the bottom?
Because that's where he started the tail of the vector from.
What?
That's fine.
Oh, it's on my boat.
Okay, so we are, let's keep looking at this. Vertically speaking, how many vectors do we have?
Vertically speaking?
Perfectly vertically,
One.
we only have one. This thing that we call Vy. So when you find this Vy, whatever it is, that'll go here. Why is Vx going to be a little more complex? Anybody calculate this one yet? This is where it's all in the picture. This is why I value the picture. What's going to happen horizontally in this problem that we have to do that we didn't have to do in the last problem?
Combine the two vectors.
What?
Combine the two vectors.
Which two?
Uh,
Give me colors.
the red one and the orange one.
Because they're both acting in the horizontal dimension. And once you combine these two, then you have Vx. Now, what can you tell me about the sign that you're going to get on this Vx here? if you use the right angle. It'll be negative. So when you combine them through addition, they're not going to perfectly cancel. It'll leave you with something, but that's what goes where this Vx is. Okay? Because you have multiple vectors in the same dimension. Most people want to take this 3.3 and immediately shove it over here into the Vx because that's what they don't have. But they don't realize this is in between dimensions. And so whenever you have vectors that are in between dimensions, you need to do this vector resolution so that you can isolate vectors in the different dimensions. And if you only have one, then it's a no-brainer. That's what your value is in that dimension. But if you have multiple vectors in a dimension, you have to allow them to like overlap with each other. Damn, it's a good problem. And this is like super basic. Okay, once you do enough of these, you understand this is the game you got to play. Okay. Yeah, if you know how to look at them, it's I gotta get the picture down. But once you draw a good picture, it kind of tells you what you need to do mathematically. That's why I'm big on the picture stuff. Okay, so that's it for today.